So, welcome to M Cubed, and this little video is all about standard deviation, from fairly simple applications to quite complicated ones. So stop watching when you feel you've had enough. Okay, so what we're going to look at in this little video is standard deviation, and really the first question you might have is, well, what is standard deviation? And what it is, it's a measure of spread, how spread out our data is. Suppose two different teachers each gave their class the same test. Right, and the first group achieved these marks out of 20, right? So if we work out the average, we get 22, 30, 41, 50, 5 boys scored a total of 50 marks, and we would get an average here of 10. Right, let's look at the second group. Right, the second group, we've got 6 boys, we can work out the average, 20, 21, 40, 60. Divided by 6, and we get the same average. Now, if we look at these two groups, they clearly haven't performed similarly at all. The first group is much more consistent. Their marks are much closer together, whereas the second group, we've got boys who've done really poorly, in fact as poorly as possible, and we've got boys who've excelled. The first group is more consistent, less spread out. The second group is much less consistent, more spread out. Standard deviation, and we've got a little symbol for it. The symbol for standard deviation is a little sigma. It's a Greek lowercase s, looks like that. All right, is a measure of spread. And if this is the standard deviation of the first group, and this is the standard deviation of the second group, sigma 1 and sigma 2, sigma 2, the standard deviation of the second group, would be much bigger than the standard deviation of the first group. Right, the bigger the standard deviation, the more spread out the data. The smaller the standard deviation, the less spread out the data. Right, let's work out now how we would calculate standard deviation. Just before we do that, I just want to show you a little simulation which shows a sort of distribution curve for some data. Okay, so this curve that's being shown here is actually what's called a normal distribution curve, all right? And it basically represents the spread of our data. It's got two sort of parameters. One is the mean, and you'll notice that if I change the mean, all right, the curve just moves along. So for example, when the mean is 3, try and get it to 3, when the mean is 3, that's the sort of most commonly occurring item, and that's kind of how a normal distribution works. Irrespective, there's this notion of standard deviation, and what standard deviation is, it's a measure of how spread out the data is. So notice for a given mean, if I change the standard deviation, if I make the standard deviation smaller, then the data is less spread out. Okay, in other words, it's more tightly packed around the mean. If I make the standard deviation bigger, the curve is more kind of more spread out. There's more data on either side of the mean than if the standard deviation is small.
Right, one of the things that we need to be good at is calculating standard deviation. And there are two ways of doing it. One is understanding how the formula works, and the second is using a calculator. And I'm going to show you both, and I'm going to show you why you need to know both. All right, so if you look at this formula gives us variance. And what it says basically for every item, we take away the mean, we square the result, we add all of them up, and then we divide by how many there are. So we basically find an average of the difference between the mean and every data item squared. We add those up and divide it out, so we get an average, right? And that gives us the variance. So the first thing in calculating standard deviation, we would need to find the mean. So for example, if I had these four numbers here, 2 and 5 is 7, and 7 is 14, 24, the mean is going to be 24 divided by 4, or 6. Right, then what I do is I take each data item, and I work out what is that data item, 2 minus the mean, 5 minus the mean, 7 minus the mean, and 10 minus the mean. Right? Those obviously come to -4, -1, 1, and 4. Now, interestingly, if one averaged those out at the moment, we'd get 0, because the positive ones and the negative ones would kind of cancel each other out. That is why we do a squaring over here. So we now square each of these numbers. So we get 16, 1, 1, and 16. We add them up and we get 34. And then we divide by how many there are. So 34 divided by 4. Right, now 34 over 4, I think, is 8.5. And that is our variance, right? So the standard deviation would be the square root of 8.5. Right, let's have a look at how we would check this out on a calculator. Right, so we go mode, stat, and we're going for one variable stats. You'll notice I've got the frequency mode turned on my calculator. That's a good idea, and I'll show you how to turn that on just now. All right, but we're going to put in our data items, 2, 5, 7, and 10. We then press all clear, and we go shift, stat, and we're going for var, which are the variables about those data items. The calculator gives us three options that we're going to use. The first one is n, how many data items there are. The second one is x bar, that's the mean, which we've already worked out to be 6, so we won't bother to confirm that. And the third one is the standard deviation, and we always use this one as opposed to this one, which is also a standard deviation, but for a different application. So we use number 3, right? And we get 2,914. Now, so that's the standard deviation, and I'm hoping that that's the square root of 8.5. If I square that result, we see that I get 8.5. So it is, in fact, indeed correct. So a lot of people will say, well, why on earth would one bother to calculate standard deviation this long way if one's calculator can do it? And examiners try to make up questions that make sure you actually understand what's going on with standard deviation. So let's have a look at two examples that I've made up. Right. So here's an example. We're not given the raw data. John calculates the standard deviation of 5 numbers to be the square root of 44. And he finds a scrap of paper from his calculation. And the question is, what number was here if these numbers, which we don't actually know the original data, had a standard deviation of the square root of 44, and there were 5 of them. So now remember, if the standard deviation is root 44, then obviously the variance, which is what the formula we get on the data sheet, the variance will be 44, right? Now there are 5 numbers. That means that the sum of the squares, in other words, this of our numbers must have been, sorry, of our numbers minus the mean all squared, that must have been 220. Because once we divide it by 5, we get 44. So these here have to add up to 220, right? And so that enables me to work out A. And so I've got 89, I think, 89, 90. All right, so I think I've got 211 over here, I think. And I hope I'm right, in which case A must be 9. Okay, so that is correct. And the only way that we can do this question is, in fact, understanding the principle. Let's have a look at an even maybe a slightly higher order level one. So here are the maths marks for a class of 23 boys, and they have a mean of 73% and a standard deviation of 10. Daniel's mark of 67% and Tim's mark of 79% are removed. What will the new standard deviation be? Now, this is quite a kind of one's got to think a little bit about this, but because obviously if marks are removed, the mean might change. But in fact, if one have a look at it, these two boys average out at the mean. Daniel's mark is actually 6% below the mean, and Tim's mark is 6% above the mean. So their marks being removed will not affect the mean. So the mean is still 73%, even when there are only 21 marks. All right. Now, what we knew is that the standard deviation was 10, all right, which means that the variance is 100, which means that when we added up all the numbers from 1 to 23, each one minus the mean, okay, we actually know that the mean is 23, squared, we would have got 2300. And the reason we need to get 2300 is that when we divide by 23, it being n, we get 100, and then when we square root it, we get our standard deviation of 10. Right. Now, if we only take this up to from 1 to 21, then what we've got, all right, we're going to get our 2300, but we now need to minus Daniel's mark minus the mean, and Tim's mark minus the mean. So Daniel's mark is 67, minus the mean is 73, and 79 minus 73. This one comes to negative 6 squared, or 36, and this one comes to positive 6 squared. So we need to take, from 2300, we need to take 72 away, and that leaves us with 2281. Sorry, it doesn't at all. It leaves us with 2228. All right, 2228, but that I now need to divide by 21, the new value of n. So what in fact I get is I get that the new standard deviation is going to be 2228 over 21, and that would be the variance. So I then need to square root it. We work all of that out, and we get about 10,3. So the standard deviations increased slightly. Right, let's take a look at interpreting standard deviation. All that standard deviation is, it's a measure of spread. So for example here, all three of these distributions of data, the green, the red, and the purple, have got the same mean, right? These are sort of normal distributions. They're symmetrical about the mean, right? But in fact, the green one has got a lower standard deviation, right? So for example, if we call this one sigma 1, that one's standard deviation sigma 2 and sigma 3, then sigma 1 is actually the smallest standard deviation. The data is the most sort of, or the least spread away from the mean. Sigma 2, the next smallest standard deviation, and sigma 3, the biggest standard deviation. The data is more spread out, right? So as a general rule, if one goes one standard deviation either side of the mean, we include 67% of the data. If we go two standard deviations, we include 95% of the data. And if we go three standard deviations, we include just short of 100% of the data. These numbers are worth remembering.